Here's a challenge. Can we train a computer to generate Shakespearean text? Let's have a go. Here's a first attempt. The knave stand style him not. Not very impressive. I generated this using exactly the same style of probability model that we've been using throughout this course so far. I designed a random variable distribution for generating values, in this case words, and then I generated a random sample. In other words, I generated a list of independent values x1 up to xn drawn from the common distribution. This is called the bag of words model. And of course, I don't need to do any work to fit the probability model for my words choice, since the best fitting random variable is the empirical distribution. In other words, I just pick words at random from the entire text. So this output isn't very Shakespearean. Can we do better? The basic problem with picking words independently is that words shouldn't be independent. If you know one word, you can make a guess at what comes next. If I say wherefore, you're primed to expect art thou Romeo? So here's another probability model. I'll just write out all of Shakespeare in a great big string, pick a random point to start, and read off a sentence from there. Confusion now hath made his masterpiece. This definitely does what I asked for. It's a random sentence. It's random because every time I run it, I get a different output. And the word choices aren't independent of each other, and it most definitely sounds Shakespearean. But it's a cheat, obviously. It only sounds Shakespearean because it literally is Shakespeare. We'd like to be able to generate random text which does both things, which can generate novel output like the bag of words model, and which can generate non-independent output like the random substring model. This is what this section of the course is all about. How we create probability models for systems of non-independent random variables. I'm using the word system fairly loosely. All I mean by it is there's some non-trivial structure here about how the individual pieces relate to each other. There are so many models that come under the heading of random systems. Any sort of simulator with random elements inside, for example like Professor Ferguson's COVID simulators or like climate models. Anything to do with text or any other sequence data like behavioral logs. Or trying to predict election results when the region-by-region polls all have correlated errors. The list is endless. We'll concentrate on two particular types of random system for now. We'll look at models for generating sequences, called Markov Chains, and we'll also look at a clean way to write out Bayesian-style models, called Causal Model Diagrams. First, one last word on Shakespeare. This is an example of the output from a neural network designed to produce random sequences with correlations. When little swain would be attained into never being fed, and who is but a chain and suspects of his death. This sort of neural network, called a recurrent neural network, is based on a probability model for sequences. Once you see what the probability model is, it's easy to just write out the log likelihood and then to fit it using maximum likelihood estimation, and then our trained model will generate new sequences just like this. Okay, on to random systems. This video isn't going to have any calculations or computations or methods in it. This video is purely about modeling, in other words, how to turn a code or text description of a problem into something that we can reason about. For the calculations, you'll have to skip ahead 2 videos. Now, one of the most important things to get right for reasoning about models is to have the right notation. Causal diagrams are a good way to show how a random system is generated. A causal diagram is a directed graph with nodes representing the individual random variables and edges saying which random variables were generated from which other random variables. More specifically, a causal diagram is a directed acyclic graph, which means there are no circular dependencies. They correspond pretty much directly to source code. Here's an example. This is the model for MP expense claims that we looked at right at the beginning of the course. There are some constants and then 3 lines of code for generating random variables. And this is the causal diagram. It just says, first we generate k, then we generate y based on k, then we generate x based on y. X is pretty trivial generation, it's just a deterministic function of y. But y is random, and so x is random. In other words, every time I run this code, I'll get a different value for x. The point is, we write out a symbol for every random variable that we're interested in, and we put in edges to show what was generated from what. The thing about directed acyclic graphs is that they can be put into order, called a total order if you remember your first year algorithms course. This means that if you see the causal diagram, and if there's text saying how each of the nodes was generated from its parents, then you can translate that diagram into code, in other words into a script to generate the whole thing. If there were cycles in the diagram, there'd be no starting point for the code, so that wouldn't work. One thing I'd recommend is marking out on your diagram all the unknown parameters. If you're doing machine learning, in other words, if you're estimating the values of unknown parameters from data, then it's good to remind yourself of where they come in. In these diagrams, we use uppercase letters and arrows for random variables and the links between them. So I'm going to use lowercase and dotted lines for unknown parameters, just to make it clear that they're not random variables. Of course, Bayesianists would say there's no such thing as an unknown parameter, there are only random variables. Here's how a Bayesian might draw a causal diagram. Here's a typical Bayesian question. I have a bias coin. I let the random variable theta be its bias. I toss it 3 times and get values x1, x2, x3, and I want to predict what will happen on the 4th toss. These words correspond to simulator code, which I've written out here. First generate theta, then generate the x values, then generate y. And here's the causal diagram behind it. The x's are generated using theta, and y is generated using theta, and y doesn't depend on x. The question text asked us, given observed values x1, x2, x3, predict y. The causal diagram doesn't encode that question, it only encodes what we might call the simulator behind the question. Once we have the causal diagram, we'll want to answer questions about the distributions of the random variables in it. We could ask for the posterior distribution of theta conditional on the observed x's, or we could ask for the distribution of y conditional on the x's again. The point is, the causal diagram describes the probability model. In other words, it describes simulator code for generating random variables. The inferences you want to make with it are a separate matter. Causal diagrams are especially good for mental hygiene. If you're faced with a giant wall of text or a mass of code, it's a good idea to draw out the causal diagram to make sure you've got everything straight. Here's an example. This is a Bayesian question from an earlier exercise. When you're faced with a mass of text like this, it can be hard to know where to start. Start by scanning through and looking for everything that might be a random variable. This question definitely has random variables m and h because it literally tells us about them. But there are some extra values here too. The question talks about the readings which we've obtained on 30 patients and also about the reading for a new patient. Let's call these readings x1 up to x30 and y. And now here's the causal diagram for how all the pieces fit together. The x's are readings from sick patients, so they only depend on m, the random parameter describing how my diagnostic test performs. The y comes from a new patient who may or may not be sick, and h encodes that status, so y depends both on the test performance m and on this patient's health status h. And the question is asking us about whether the new patient is healthy or sick. In other words, about the distribution of h conditional on the observed data, conditional both on the new patient's reading y and also the readings from the other 30 sick patients. It takes more time to describe the setup in words than it does to draw the diagram and write down a maths equation. Okay, let's look at another example. This one is called a random walk. We have a stoat scampering about, and let xn be its location on day n. Here's some code to generate its path. The yield statement might not be familiar to you. It's just Python's way of specifying an infinite lazy list. We call the RW function, RW is short for random walk. We get back an infinite list object, and we can request the next item in the list by calling next on it, and then we can, for example, plot the values. In this code, on each day, we generate a normal random variable, and then we add it to x. In other words, the location on day n+1 is generated from the location on day n. So the causal diagram is just a straight line. Each xn+1 is generated directly from xn. A probability model like this, where the causal diagram is a simple line, is called a Markov chain, and we'll go into them in a lot more detail in the following videos. First, here's another example. This is a souped-up version of our Stokes random walk. Let xn be its location on day n as before, but let's also imagine that we have some other sensor, for example a low-res camera, that tells us some indirect noisy readout of its location. Let this noisy readout on day n be yn. This is how we'd express it in the causal diagram. We're saying that each yn is generated based on the corresponding xn. The question asks us, if we were told the y's but not the x's, how well could we infer the Stokes location? For example, if we have a string of whitish colours followed by bluish, we know it must be somewhere where there's mountain near to water. The next practical assignment will ask you to do just that. We'll need computational Bayesian methods from earlier videos, and we'll need some math tools for reasoning about conditional probabilities and causal diagrams, and that will be the topic of the next few videos. For these math tools, the most important thing to get straight about causal diagrams is that they're just shorthand for writing out a probability model, or more precisely, for writing out the joint likelihood. There's nothing magical about them, they don't answer questions for you, they're just a visual way to represent the joint likelihood of a collection of random variables. Here's an illustration. The causal diagram x goes to y goes to z just means first generate x, then generate y based on x, then generate z based on y. In other words, the joint likelihood is the product of three terms, one for each of the generative steps. Here are two more examples. In each case, the joint likelihood is just the product of terms, one for each random variable, and each random variable is generated conditional on its parents. When you write out a causal diagram, you're really specifying what your probability model is. As we saw in the earlier video on Bayes' rule, the starting point in any probability model is to declare, this is what I want my joint distribution to be. The causal diagram is nothing more than a way to encode that. The notation gets a bit heavy going when there are lots of random variables around, so I'll often use an abbreviated notation where I drop the subscripts and I just write, for example, this third factor here, likelihood of little x given little m, as a shorthand way of saying the likelihood for random variable big X of value little x given that big M is equal to little m. In the next two videos, we're going to look at Markov chains where the causal diagram is an infinite line, like the random walk example. And then we'll come back to more general causal models to see the typical steps for reasoning about them, so that you're ready to solve the hidden Markov problem for finding the location of our friend, the scampering stoat.